Good afternoon, student. Today I am going to deliver a important lecture on comparisons of RRK and RRKM theory. Friends, while preparing this special lecture on comparison of RRK and RRKM theory, I have referred large number of books, monographs, as well as the original research paper of Professor Marcus and other scientists. And I noticed that most of the derivations are quite complex for the M.Sc student, particularly chemistry student. Then I thought that I must prepare a student-friendly lecture so that student can understand the basic principle of RRKM theory. You will be glad to note that for the last few years, as per your course content, I have prepared large number of video lectures related to all these unimolecular theory. I have prepared a separate lecture for Lindemann theory and then Hinshelwood theory, as well as also RRK theory. And I have also prepared, I think 2 years back, I also prepared a separate lecture on RRKM theory. But I have received large number of message from my M.Sc students and research scholars that please do prepare a very simple lecture and in mixed language, Hindi and English, so that this most important theory can be understood. And one thing is very common, you know that these all four theories are interrelated. But today I am planning to discuss first some application of the RRK theory and what are the problems of the RRK theory, because there is a separate lecture for the RRK theory. So I will not go into details of the RRK theory, and then I will discuss the salient features of the RRKM theory. As I told you that this history of unimolecular theory is very, very important and interesting. And if you read the biography of Nobel laureate Professor Marcus, because he worked with another scientist, Professor Rice, OK. Rice, who initiated that RRK theory, that this period, that means in between 1920 to 1952, like that, is a glorious period of unimolecular theory. And I have prepared a journey, you see. As you know that the starting point is Lindemann theory, and of course the ultimate theory is the RRKM theory, which was developed in 1952. Although he has started his work in this University of Chapel Hill University of North Carolina in Chapel Hill during 1949 and 1951, and ultimately published in 1952. So therefore we consider that RRKM theory is 1952 theory. Now, as you know that in your course you are studying the Lindemann theory, then you study the Hinshelwood theory using the statistical thermodynamics, and then of course the intramolecular energy transfer, and then the RRKM theory. But in between these three theories, there is another important contribution that is called the N.B. Slater. He has also written a book. And after the discovery of RRKM theory, there are some problems regarding the calculation of pre-exponential factor, which is very high, like 10 to the power 13 second inverse 1, and how that energy is distributed. Then of course Slater has done some very good work using this very simple example. You all know that unimolecular theory, formation of this ethyl radical. Actually he improved, and this is the starting point of this RRKM theory. Suppose he has taken a compound and there are 18 normal modes of vibration. But the problem was that all these modes of vibrations are not involved in this chemical transformation. There are only 12 modes have been used. So that is very important. In RRK theory is not very realistic, because a molecule does not instantly randomize energy among all its vibrational modes. किसी तरह से ऐसा लगातार ये नहीं हो सकता है. But the reaction depends, because there are two stages, you know that. One is energized state, another is the activated state. So you have to calculate the actual intramolecular energy transfer, that how that energy distribution in different modes, and that has to be solved by the different theories. And that is sometimes we can call it the quantum mechanical theory. Now, as you know that whenever I start any teaching, I referred large number of research papers, and fortunately I have brought all those original research papers, and there are large number of research articles, even Nobel laureate lectures, Marcus, because he was awarded Nobel Prize in 1992 for electron transfer reaction. But you see, why it is called the RRKM? Because it is a advancement of Rice, Ramsperger and Kallol, and he used this theory and he blended with transition state theory. So sometimes it is called microcanonical transition state theory. And there is a very beautiful article, you see, perspective on the M in RRKM theory. And this is the one of the most important paper. Those who are interested, जिनको बहुत ज़्यादा आगे देखना है, क्योंकि जब मेरे पास स्टूडेंट्स का फोन आता था कि सर RRKM थ्योरी को बहुत इजी ढंग से आप कैसे समझाएंगे, so then I referred large number of research papers, and I have prepared a very simple method, and this is the first paper on the unimolecular reaction based on the RRKM theory by the Marcus and OK Rice. OK Rice, actually Marcus जो है वो नॉर्थ कैरोलिना यूनिवर्सिटी में एज ए पोस्ट डॉक्टरल फेलो के रूप में काम कर रहे थे ओके राइस के साथ, So he started this work using the methyl iodide, and as you know that same thing, A plus B like that. And bear in mind, आप लोग ये मन में रखिए कि there is no difference between the mechanism of RRK theory and RRKM theory. Okay. So this is this paper is this like that. This is the actual this paper. Second paper which I referred, that because you know that my title is comparison of RRK and RRK theory, RRKM theory. So I must confess that I have taken some of the notation from this research paper published in Journal of Physical Chemistry by these two scientists, Gordon Skinner and B.S. Ravindrich in University of Washington. And in addition to that, I have also referred the पेपर जिसके कारण हम बोलते हैं कि RRKM थ्योरी जो है 1952 में, because he has published this paper, that is in 1952, the Journal of Chemical Physics, single author paper, unimolecular dissociation and free radical recombination reaction. But you are the student of M.Sc final chemistry, M.Sc previous chemistry. I thought that if I use the derivation of this theory, so I think आप लोग के लिए ये थोड़ा सा तकलीफ होगा. So therefore I have also referred some of the textbooks as well as the books related to unimolecular theory. And मैं आपको पहले बता देना चाहता हूं, because the problem is that all these theory, RRKM theory or Lindemann theory and Hinshelwood theories are available in the textbook. But so far as my simple knowledge is concerned, I have not seen the complete derivation of RRKM theory in the textbook. Therefore, I have searched some of the literature, and some books are available in our Pandit Ravi Shankar Shukla University library. तो मैं जो इन सारे बुक्स या रिसर्च पेपर्स को देख के कंसाइज लेक्चर तैयार किया जो आप लोगों को इजीली समझ में आएंगे. And for that I have also taken the books of molecular reaction dynamics, Raphael D. Levine. There is a part on the RRKM theory. Similarly, I have taken this theory of unimolecular reaction, Wendell Frost. अभी मैं आपको समझाऊंगा कि आप लोग कंफ्यूज मत होइए कि कौन सा नोटेशन हमको कहाँ पे यूज करना है, because it is very similar to RRKM theory. Then I also referred a very good book, Unimolecular Reaction Dynamics, Theory and Experiment by Hayes and Thomas Baer, as well as this book, Unimolecular Reaction, a concise introduction by Prof. And also, as usual, I have also referred the chemical kinetics by K.J. Ledler. Very elementary information about this. इसलिए आप लोग थोड़ा ध्यान से सुनेंगे. मैं बहुत सिंपल मेथड से इसको करने की कोशिश करूंगा. And whenever such type of theory exists, the first part is that you have to write the salient features of this theory. अर्थात सबसे पहले आपको RRKM थ्योरी के salient features को लिखना है. Then there are certain assumptions, there are some energetics diagram, and then you have to derive the final equation. You can use some simple mathematics related to integration by parts, like that. So the question is that I have written the comparison between RRK and RRKM theory. I will also explain very simply some application of the RRK theory because it is very similar. And there are two derivations, one is high pressure and another is low pressure. But again, I will start from this Lindemann theory. You all know this thing. K1, K inverse 1. Then K2. You all know this thing. 1 plus K2, K inverse 1. That is our Lindemann theory. And here, all these rate constants are associated with some energy. So when rate constants are associated with energy, so it is called microcanonical rate constant. But जब हम experiment करते हैं, so you all know that we determine the rate constant, which is temperature dependent. So that is canonical rate constant. So in RRKM theory में हम लोग एक formulate करेंगे how microcanonical rate constant is related with the canonical rate constant. Now when I derive that RRK theory, आपको सब मालूम है, there are two methods. First I derive this K1 and K inverse 1 using statistical mechanics, and that the values of K1, K2 I have determined from the Hinsel-Wood mechanism, and this K2 I have derived from statistical thermodynamics, and that is, you know, this thing. So what is the difference between this RRK and RRKM theory? In RRKM theory, we will again determine this K1 divided by K, which is the probability density, sum of the states with energy E or change in energy class by some methods. And we also determine that K2E by some method. And that part 1 K inverse 1 is collisional deactivation. Collisional deactivation. So first difference is that it is not very realistic RRKM theory. Again, when I derive this equation, we will get just a formula just like your Arrhenius equation. And in why I am saying दोनों का mechanism same है, क्योंकि up to Lindemann theory or Hinsel-Wood theory, there is only one state that was called energized state. But in RRK and RRKM theory, there is an additional state that is called activated state. So RRKM theory में the vibrational frequency or the vibrational energy can be treated explicitly for energized state and for activated state. ये दोनों का difference है. मैं अभी जब derivation करूँगा तब आपको बताऊँगा. And if anybody can ask you, sir, what is the problems of that RRK and RRKM theory? Why? And if you see the year, RRK theory was developed by RRK Rice in 1928 or 27, whereas he developed this theory again with the work with that Rice in 1949 or 50. करीब 20-22 साल का difference है. And when I have seen that research paper, the comparison, they have given large number of rate constants. But the problem was that in RRK theory, if I am able to calculate the pre-exponential factor, जो कि मैंने आपको introduction में बताया, जिसकी value is 10 to the power 13. it is very high. So therefore मार्कस ने RRKM थ्योरी का डेवलपमेंट किया. Now, as you know that what is the final formula of the RRK theory? So it is very similar to the, there is only activated and this part is the energized part for high pressure and low pressure, you know. मैं इसको डिराइव करूंगा तब आपको समझ में. So it is not very satisfactory. Again, in both the cases, unimolecular rate constant. But the final formula of RRK theory, RRKM theory is very simple. स्टूडेंट उसको याद रख सकते हैं. And if you remember the ट्रांजिशन स्टेट थ्योरी, क्योंकि मैं थोड़ी देर पहले आपको बताया कि जो RRKM थ्योरी जो है वो उसको माइक्रो कैनोनिकल ट्रांजिशन स्टेट थ्योरी बोला जाता है. क्योंकि अगर हम ट्रांजिशन स्टेट थ्योरी की फॉर्मूला को देखेंगे तो इट इज के बी टी, आपको याद अगर होगा, माइनस डेल्टा जी एक्टिवेशन और वट एवर टी, आर टी और के टी. And if you see the final RRKM theory, again the same thing is there. But there is the additional part. I'll explain what is that Q and Q activated and Q thing. And this is the critical energy, which is very important. मैं अभी डायग्राम से आपको समझाऊंगा. तो दूसरा डिफरेंस क्या आ रहा है RRK का? RRK थ्योरी में केवल हमको K एक्टिवेटेड मिल है. But there is no involvement of the partition function. So this is the partition function of transition state, and this is the partition function of vibrational and internal translation. Because when there is a collision is common for all these theories. There is a change in internal motion, vibrational motion, and the rotational transformation and other things. So therefore, this is the final equation. I will derive it, and here I have written this unimolecular rate constant with respect to temperature, that is called the canonical rate constant. Don't confuse with this rate constant; it is Boltzmann constant. ये confuse मत होइए. And in some books it is, you can, ऐसा भी आप लिख सकते हो. आप कई जगह में जब हम डिराइव करेंगे तो हम इसको आप समझाएंगे आपको. What is critical energy and other things, that is very important. It depends कि आप उसको कैसे आप उसको करेंगे. So this is the final thing. अब हम आते हैं, this is very important diagram, and if you understand this diagram, you can easily derive that RRKM theory. And I can also tell you that there are two parts. One is the energized part. So that is, in some books it is also written as E star, you can also. Or it is a reactant part. And this part is called the transition state or the activated part. Clear? There are two parts. Energy responsible for this reactant is E, capital E, which is of course comprises of vibrational and translational rotational energy. And this part is the ground state 0 point energy of that reactant. And this point is very important, where I can write the one star, that is called point of no return, because then of course there are energy can be divided into two parts. One is called active energy and another part is called the inactive or adiabatic energy. How do you define? कैसे बताएंगे? जो एक्टिव एनर्जी जो है, इट मीन्स दैट पर्टिकुलर एनर्जी कंट्रीब्यूट फॉर द ब्रेकिंग ऑफ बॉन्ड, मतलब केमिकल रिएक्शन हो रहा है. बट व्हाट अबाउट दैट इनएक्टिव पार्ट or adiabatic part? That energies are not contributing for the bond. I am not saying that it is not absolutely not possible, but they are not involved or very little contribution, very little energy to the breaking. And so ये भी एक दोनों RRK का और RRKM का एक डिफरेंस आपके सामने दिख रहा है कि RRK थ्योरी में ये डिस्टिंक्शन पॉसिबल नहीं था, एक्टिव इनएक्टिव. RRKM थ्योरी में ये पॉसिबल है. दूसरा डिफरेंस ये है कि द डिफरेंस बिटवीन द 0 पॉइंट एनर्जी ऑफ रिएक्टेंट एंड 0 पॉइंट एनर्जी ऑफ द एनर्जाइज्ड स्टेट, जो बहुत इंपॉर्टेंट है, जिसको हम लोग बोलते हैं क्रिटिकल एनर्जी. ये आपको यहाँ, माई स्टूडेंट्स हैव प्रिपेयर्ड दिस थिंग, सो देयर इज नो प्रॉब्लम. So you can write actually here also this part. This part is important. So you can call it deactivated. And so how can I calculate this thing? So that means E minus E0 critical, which is very important. Without this reaction is not possible. That is equal to E activated, and that can also be, I can write E rotational plus E vibrational. You follow my point? Because if you don't understand this diagram, that is called the, sometimes it is called the energetics or intermolecular energy transfer diagram, or sometimes in some books, some research paper, some monograph, it is called एनर्जी लैंडस्केप. तो आप मतलब इसको अगर हम इस तरह से भी आप लिख सकते हैं, बिकॉज इट इज जस्ट लाइक दिस इज यू नो दिस इज so this point is very important. And then finally, after the derivation, now this part is actually active part, and this part is inactive part. Sometimes it is called kinetic energy. So it is internal energy, internal motion, vibration and translation. So I think you follow this diagram. So before deriving this equation, you must understand the difference, because when I derive this, आपको समझना पड़ेगा कि ये कहाँ से आ रहा है. Now the salient feature. First point is that in the RRKM theory, क्योंकि आपको मैं फिर से बता रहा हूं, if you see my title, it is the comparison of RRK and RRKM theory. आप कंफ्यूज मत होइए, क्योंकि RRK थ्योरी का मेरा अलग से लेक्चर है, RRKM थ्योरी का भी लेक्चर. मैं इसको कंपैरिजन बताने की कोशिश कर रहा हूं. So first point is that the proper quantum mechanical treatment of vibration and rotation. And I have already discussed the role of active energy and the role of inactive energy. And basically, if it is the inactive or adiabatic, जैसा मैंने आपको बताया, there is no change in quantum state. There is no change in quantum state. So therefore, ये जो inactive molecule है, ये bond breaking formation में involve नहीं होता है. Whereas the active mode जो है, yes, there is a possible of the exchange energy. And you know that we are considering here only translational, not translational, vibrational. as well as the rotational energy. And as I have already told you, that the energy in the activated complex is very important. That I have already discussed with you. I will not repeat these things. Another feature, RRKM theory, the first line you must write. It is an excellent framework for a qualitative as well as semi-quantitative, because when you derive the rate constant and other things, for complete understanding of the unimolecular. And I have already told you many times that, and if you read this biography, you will find that he blended RRK theory with the transition state. So therefore it is called the microcanonical transition state theory. I have also told, आपको मैंने फिर से बताया कि दो स्टेट है, एनर्जाइज स्टेट एंड एक्टिवेटेड स्टेट. इस आरआरकेएम थ्योरी द्वारा दोनों स्टेट को, जो वाइब्रेशनल फ्रीक्वेंसीज है, वाइब्रेशनल एनर्जीज को हम कैलकुलेट कर सकते हैं. एंड वेरियस नॉर्मल मोड्स ऑफ वाइब्रेशन एंड रोटेशन contributes the reaction. That is the active part. Now there are salient features that when there is a collision, so it will excite the internal degrees of freedom and there is a vibration and rotation of the molecule. And clear-cut distinction. And this collisional activation followed by intramolecular vibrational relaxation leading to the transition state. And considering the explicitly individual vibrational and rotational modes and included the 0 point energy. जो मैंने आपको जो एनर्जेटिक्स टेबल में बताया उसी चीज को अगर आपको लैंग्वेज में लिखना है तो यू कैन राइट लाइक दैट. And it assumes that energy inside the molecule is shared among all its internal motion. And the reaction rate depends on how many ways that energy can be arranged. And of course, without the involvement of the critical energy, E0. So therefore, when we will integrate it from that critical energy to the infinite, that is our objective. So now I am coming to the derivation. Now in derivation, there are two parts. Before I do the derivation, I must tell you that how we determine this K1 and K inverse 1. First part. And then of course K2. तो थोड़ा याद रखना पड़ेगा. So what do you, अब यहां से आपको कंफ्यूजन स्टार्ट हो जाता है. Now सबसे पहले मैं आपको समझाऊंगा कि ये दोनों को हम कैसे निकालेंगे. And one that is called the Boltzmann distribution. Now you can, some books it is written like that, capital P, E and T, because one is microcanonical and that can be determined. So that is to be calculated. That means there is the ratio between the canonical state as well as the microcanonical state. That is the first part. How can I determine these things? Let me. So again now regarding the notation, इसमें थोड़ा confuse आप मत होइए. I am here using, because whenever I write the probability density. In some books, it is written like rho type of thing. But here, I am using that sum of the states अलग अलग एनर्जी का स्टेट है, इसको मैं कैपिटल एन और ये एनर्जी स्टेट इस तरह से मैं शो करूंगा. तो सबसे पहले आपको यहाँ कंफ्यूजन नहीं होना चाहिए. So here you see that like that. Second, that the another factor, that is K2E. जब आप रिसर्च पेपर देखेंगे इसका भी बहुत सारे फॉर्मूला है अलग अलग. ना सबसे पहले तो आपको समझना पड़ेगा व्हाट इज द डिफरेंस बिटवीन दिस डिस्ट्रीब्यूशन and that G factor. So the distribution means the density of the state, and this K2E जो है उसमें कुछ बुक्स में ये, क्योंकि मैं कई रिसर्च पेपर फॉलो किया हूँ, तो दैट इज डिनोटेड एज G. आप यहाँ पे एक्टिवेटर्स लिख भी सकते हैं एंड देन यहाँ पे आप N इस तरह से लिख सकते हैं. यू कैन राइट नॉट N, E divided by Planck constant. In some books again here it is a probability, but here I will write here N. So frankly speaking that I am here using the G, capital G, and states of the activated complex transition state with energy above the barrier. अब सवाल ये उठता है कि from where I get this value, that means in somewhere the density is written like that, N E exponential E by KT divided by capital Q. So in my next slide, I will explain these things. Now, कहाँ से आप डेरिवेशन स्टार्ट करेंगे? You will start the derivation from this Lindemann equation, again original equation. इसलिए मैं थोड़ा हिंदी में आपको समझाने की कोशिश कर रहा हूँ, because this is the starting point of derivation of RRK into the simplest method. I think you have to remember this thing. And what I am doing, I am writing these values of K1 and K2 as well as K2E, and it is a micro canonical rate constant because it depends upon the energy. तो हमको कंपैरिजन करना पड़ेगा. एक कैनोनिकल रेट कांस्टेंट विच इज टेम्परेचर डिपेंडेंस, यहाँ पे हमको इंटीग्रेट नहीं करना पड़ेगा फ्रॉम E0 to infinite. But when I am considering the micro canonical, so the distribution of energy should be calculated. So in first point of the RRKM theory, I have to write this thing. Again इसमें स्टूडेंट का कंफ्यूजन होता है कि somewhere if I write the density, probability density, it is again as just I have written N, यहाँ पे एक्टिवेटेड देंगे तो चलेगा E by K. In some book, as I told you, that the sum of the state or the density is based on the rotational energy as well as the vibration. In some book, you will find that here is vibrational. So I have to write n E vibrational exponential E vibrational divided by k. And another is the rotation. So I can write and divided by q vibrational partition function. और अगर हम रोटेशन का लिखेंगे तो सेम इक्वेशन आई राइट रोटेशन एन ई एक्सपोनेंशियल ई रोटेशनल डिवाइडेड बाय के डिवाइडेड बाय क्यू रोटेशन. यू फॉलो माय पॉइंट. बट यू विल गेट कंफ्यूज अगर आप रोटेशनल का अलग करेंगे वाइब्रेशनल का अलग करेंगे. इट इज बेटर to write a general equation where you should not worried about the whether it is a rotational or vibrational, a rotational partition function or vibrational partition. Instead of writing small q, आप यहाँ पे simple capital Q लिखेंगे. I will not discuss the what is the rotational or how to calculate the partition function. Now second, so therefore what I have written, this Boltzmann distribution is equal to NE, which is the sum of the states, exponential and this Q, and that Q denotes the rotational or vibration. तो आपका derivation एकदम easy हो गया. दूसरा, what about the K2 E? So that is G. कुछ बुक्स में ये दूसरे ढंग से लिखा हुआ है N minus N0, right? But you can write G. Then E minus E0, you know. If you see that diagram, you know that diagram, energetic diagram, point of no return divided by Planck constant and N. So I have to substitute these two values in our Linemann equation and this integrate. That's all. That is the simplest thing. And this again I am just citing the G. स्टूडेंट को याद करने के लिए G is the total number of states, और जो प्रोबेबिलिटी डेंसिटी में हम लोग लिख रहे थे एनी, जी की कुछ बुक्स में ये ऐसा सिग्मा, इट इज द डेंसिटी ऑफ द स्टेट. इसको समझने की कोशिश कर, दोनों में डिफरेंस G एंड states per energy. How many ways the molecule can have the energy? So therefore its dimension is energy minus 1, inverse 1. So it is the number of quantum states per unit energy. Okay? And as I told you that how can we write this thing, formula? So it is very simple that, and it is available in your book of this Ledler also, chemical kinetics by the Ledler, that if I just, why I have used this thing in first case. Now here देखिए ये मैं लिखा हूँ E and T, मतलब हम रिलेशन किसका निकाल रहे हैं, कैनोनिकल और टेम्परेचर माइक्रो कैनोनिकल. So when it is a micro canonical, no question of energy distribution. So therefore simply I have written N E exponential E by K. And when I am talking about the micro canonical, हमको energy देखना पड़ रहा है कि from where to where. So that this formula is this. And you know that this formula is nothing but the partition function. Partition function, how energy is distributed. Rotational partition function, vibrational partition function, electronic partition function. So I have written here 1 by E. So therefore I have written कि कहाँ से ये formula आया. Now I am coming to the derivation part. बोर्ड में इसको derivation of RRK. Simple derivation. So let me start with this thing. K1 of again we can start from that limit. You cannot avoid this thing. Energy, I am not written the energy. Of course, E is here everywhere. Here is also E, I am not written. Or here I can write the probability density. Here I can write G. E minus E0 you can write activity. N H. And you know that I have just the value. So what is that? Ne exponential minus E by kBT or kT you can write like that, divided by Q, the values of this probability, and this value. I can and denominator is 1 plus K2 and I can omega, collisional reactivation. So very simple, and I have to integrate it from E, of course, activated to infinite. That is our objective. So I will do for high pressure only today. High pressure. So you know that high pressure, this part is collisional deactivation part can be avoided. So I'll only concentrate on this part. So this I can, of course, K1 like that. So first what I can do, U is a constant, H is a Planck constant. So what I can do, 1 divided by Q and H. And again I am saying that I am using the simplest method. सबसे सीधा मेथड से मैं इसको करना चाह रहा हूँ. तो देखिए मैंने इसको ऐसे लिख दिया, Q and H, नीचे का डिनोमिनेटर गया, आपके पास बचा G. ऐसा लिख सकते हैं, नहीं भी लिख सकेंगे, कोई हद नहीं है. E0 आप एक्टिवेटेड का साइन दे भी सकते हैं, नहीं भी देंगे कोई प्रॉब्लम नहीं. देन एक्सपोनेंशियल माइनस E के बी लिख सकते हैं और के टी यू कैन, बिकॉज आई एम डूइंग इंटीग्रेशन, सो आई कैन राइट दैट. So you know that, just see it very carefully. I can use this red color or some other color. That we know that this, if you see that again, that energy diagram. So, because if this is main energy and this is E0, I have already shown you, and this part is complete part. So E minus E0 be activated. So in that place, I can write G and you see, and now look at here. S because E माइनस, इसको थोड़ा ध्यान से देखिए, E0 is equal to, see it very carefully, or I can write in white. So what I can write, E is equal to, अच्छे से देखिए इसको, E activated plus E. That is, critical energy is very important, you know. So what I can do, ये सब है इंटीग्रेशन का, वो तो है ऑलरेडी. Why I have chosen this 0, I have already written in my, when I solve this RRK, because E is equal to E infinite, that converted into E alpha indefinite. So that E is equal to, E star is equal to 0. So what I can write, G, in some derivation, in some books it is written like epsilon, no problem. But here I have written G. Then exponential minus, you see here, what I have written here, I can write written E activated plus E0. Divided by KBT or whatever. And now it is everywhere where I am doing activity. So one QA. Now I can write like that, exponential minus E0 divided by K. So हमने बाहर कर दिया. Now I will do the for biology student or other student, those who don't understand the mathematics, although it is very simple, I'll explain. But जो इसको नहीं करना चाहते हैं, they can directly write, but I'll solve it, don't worry. This whole integrand can be written as KBTQ, because we are talking about the activated state. So therefore, Very simple derivation. What I am getting finally, K1 is equal to this KBT 8. You see here, Q activated divided by Q. This Q is also there. Exponential minus KBT. This is the final equation of RRKM theory. Very high pressure. But question arises that how can I solve this thing? Now let me compare with this thing. You know that there are two parts. Just it will take 5 minutes. There are two parts. One part is this part, another part is this part. So that is called integration by parts. You all know UdV. First function, integration of set minus You follow my point? I have already derived the final equation for the high pressure. Very simple method. You can, if you want to derive it by other methods, you are most welcome. You can see all these research papers. But this is the simplest method for the M.Sc first semester student, first or second semester student. Simplest method. Now, how we do it integration by parts, I am coming to that point. Because you know that here I can take U is equal to this G E part. And as you know that I can write this DE, DG, and DN. So I can write this is actually N DE. I can write like that. But now the second part. What is the second part? Second part is that is the U and dV part. Integration of exponential minus E KBT and D. So you know that if it becomes simple, if I take that A is equal to 1 by KT. A is equal to 1 by KT, and I think I can E star is equal to X. So what I can do, you know that integration of exponential minus AX dx minus 1 by A, isn't it? Plus C or what? I am doing nothing. I am doing just integration by part in order to get the final equation. Although I have already derived it. So I'm sorry for the biology student क्योंकि उसको नहीं समझ में आ रहा होगा. So what I am getting here 1 by k. So it is minus kbt, an exponential minus e star divided by kbt. So I am getting both the value du and dv. So I have to write this in my final equation. What is our final equation? uv equals 0 to infinity. So the first is that just last stage. Ge minus kbt. Ge minus kbt. Where 0 to 1. And because there is a minus in the plus kbt, why it is, so you can call it what, आप इसको बाहर भी निकाल सकते हैं, आपके पास ये आ जाएगा. केबीसी को बाहर कर दीजिए, केबीसी को बाहर कर दीजिए. So this part actually that is called the boundary condition. बाउंड्री कंडीशन का मतलब आप देख रहे हैं कि अगर ई इसको हमने इन्फानाइट कर दिया, एक्सपोनेंशियल जीरो हो जाएगा, तो दैट इसके भी वैल्यू जो है जीरो हो जाएगा, दैट पार्ट. एंड दिस पार्ट यू नो दैट this is nothing but the partition function. So it will get finally what I am getting kbt and q, kbt and q, kbt and q. So what was our main objective? Main objective was K1. We have already 1 divided by Q H exponential minus E0 kBT. That is all. And that integration part, or whole integration part, whatever was there. GE activated exponential minus and D activated. एंड पार्टीशन इंटीग्रेशन बाय पार्ट जब हमने किया तो आपके पास इस पूरे पार्ट का जो रिजल्ट आया वो है तो 0 के बी टी एंड सी ऑफ कोर्स एक्टिवेटेड. So finally K1 is equal to, ये आप यहां ले आइए, ए बी टी एच पहले से लिख दीजिए, क्यू this divided by simple q, whereas exponential minus E0 divided by ABT. Of course, for high pressure, मैं बार बार उसको बोल रहा हूँ, is not low pressure, that denominator cannot be low, but low pressure value is very simple, where we need the capital Z and like that. So, what is the comparison? Here if I write RRK, you are getting, of course high pressure में आपने देखा and here is RRKM high pressure. I am getting KBT at so the basic difference is this two. This is called the micro canonical transition state theory, because in transition state theory this part is same. Now in some books or some authors and some research paper, this Q is the partition function for transition state. Partition function for transition state. And this Q can be bifurcated in small q rotation, small q vibration for internal motion. So that is the final, very simplest. If you see my original RRKM, which I had prepared in 2 years ago, that time I also used one master equation in the angular momentum. That is also possible, but this is the simplest for the ordinary students and other things. So if I just read original knowledge. Now, so before thanks again, I am just going to this my all original paper. Final equation. Yes. But here, why such type of transition is required? Because in one case, that is canonical. This is now because from K bracket E, microcanonical to canonical. So you see here, this K Boltzmann constant, Ph Planck constant. This red Q is the activated partition function for this, and this. You can write E star also, that, but that's critical. So this is the final equation of RRKM theory. Thank you very much. I am really grateful to the Professor Balwant Singh Thakur, the head of the Department of the Mathematics, School of Studies in Chemistry, School of Studies in Mathematics, Dr. Jipti Thakur, Mr. Indra Kumar, and my student Abhishek Satendra for providing me this lecture capturing facilities of Pandit Ravi Shankar Shukla University. And with the help of this lecture capturing facility, I have prepared more than 100 lectures. Thank you very much.